Okay, welcome to lesson 4 of module 5. This lesson's titled More Examples of Functions. So in this lesson, we're going to see more examples of real world functions. Functions are used in every discipline, science, business, math, obviously, and they're all over the place. We're even going to see some examples of functions that don't use numbers. So functions without numbers in this lesson, and functions that there's no way to assign a mathematical rule to it, like an equation that describes the function. And the other thing we're going to see is the difference between what we're going to call discrete and continuous functions. So we'll be defining that as we go along. So let's just go ahead and get started. So this diagram here shows a couple of tables that look very familiar. It's the candy example that we've been using for 3 lessons now, and also a time distance table that is a function. So when we look at these 2 tables, I'm going to ask you to just examine them and then talk about what are the differences between these 2 different situations, these 2 different uses of functions. So go ahead and pause and just think about that for a minute, and then we'll continue our discussion. So if you remember when we were talking about the function in table A, we said that the inputs, the x, had to be greater than or equal to 0 because you can't have negative bags of candy. And more than that, we said x has to be an integer. And since it's greater than 0, it has to be a positive integer. We can't have any fractional bags of candy that we're selling in this situation. So x is has to be a whole number, or we can think of it as a positive integer for this function to make sense. Okay, which also meant that our cost was also going to be positive, but we're mostly talking about the limitations on the input here. But for table B, we don't have that situation. In table B, x also has to be greater than 0 because it's a unit of time. We're not going to have negative time, but x doesn't have the restriction that it has to be a positive integer. It doesn't have to be an integer or a whole number. We could have these half seconds going on, or even quarter seconds, or tenths of a seconds, or hundredths. So there's an infinite, even between 0 and 4 seconds, there's an infinite number of points of time that we're talking about. So we call table B continuous. Let me get another color here. So we're going to call table B, this is a continuous function, because the inputs, are all the numbers on the number line here between 0 and 4. So it's a continuous function. There's an infinite number of inputs. But the function in table A is discrete. I don't really have room to write it. Let me see if I can move that around. So the function, the function is what we'll call discrete. And discrete is a word, you can look it up. It just means separate or distinct from something else. So you could think of these bags of candy, the numbers for the input as being discrete, 1, 2, 3, whereas the inputs for the function in table B just are continuous. Okay, so those are two different types of functions, and you've seen examples of both of those. All right, so let's look at your classwork here, example 1 that you have in your notes. If 4 copies of the same book cost $256, what is the unit rate for the book? So the unit rate, the rate for one book, we would be dividing, right? So $256 for 4 books is going to simplify to $64. And if these numbers look familiar, it's because they are. $64 for one book, right? So the unit rate is just $64 per book. I'll write that. $64 per book. So when we did this, when the 256 was feet and the 4 was minutes, then it would have been 64 feet per minute if it was constant rate. Okay, so this is a constant rate problem. All the books are going to cost the same. So we could ask, what cost does the function assign to 3 books? Okay, well first let's write the function rule. This one we can write a function rule. The total cost, y, is going to equal $64, which is the unit rate, times the number of books that we get. Okay, so there's our function rule. The input is the number of books, and the output is the total cost. So what number does the function assign for 3 books? So if x is equal to 3 books, whoops. If x is, sorry, I'm up in the corner, so I'm turning the page. Don't mean to. If x is equal to 3 books, then y is equal to 64 times 3, which is 180 plus 12 is 192. $192. Okay, and so I could ask, what about for 3.5 books? What if x is equal to 3.5? Okay, well, I can put that in my function, and it would tell me that y would be 3.5 times 64, which is $224. Okay, so I could put that in my function, but it doesn't make sense, right? They're not going to charge me for half a book. I can't buy half a book for half the cost of a book. And so we would say that this function is a discrete function. This function in example 1 is discrete. Sorry about my notes. They're all over the place, but I'm sure yours are much more organized. Okay, so this is a discrete function because the inputs have to be individual numbers, whole numbers, and there's gaps in between our inputs. Okay, so it's not continuous because we can't buy a fraction of a book. Okay, so this is a discrete function. Okay, so let's look at example 2. Here's also an example from the last lesson. Water flows from a faucet at a constant rate. That is, the volume of water that flows out of the faucet is the same over any given time interval. So 7 gallons flow in 2 minutes. Determine the rule that describes the volume function of the faucet. And we did this, and we found that the function was y is equal to 3.5 times x, because 3.5 gallons of water flow out every minute. And so if we multiply that times the number of minutes, which is what x is, then we get the total volume y that comes out of the faucet in x minutes. So the restrictions on x were that x and y be greater than or equal to 0. You can't have negative volume, you can't have negative time. So would this be a continuous function or a discrete function? This would be a continuous function because there would be no gaps between the possible inputs. This is a continuous function because our times we have an infinite number of inputs and they're right up next to each other. Okay, so continuous function. Here's an example. Example 1 is an example of a discrete function. Okay, so here's another example of a function, and this is something that you may have done in science class, maybe in 6th grade. You looked at the rate that something cools. So let's go ahead and read it. You have just been served freshly made soup that is so hot that it cannot be eaten. You measure the temperature of the soup and it's 210 degrees Fahrenheit. Since 212 degrees is boiling, there is no way that it could be safely eaten yet. 1 minute after receiving the soup, the temperature has dropped to 203 degrees Fahrenheit. If you assume that the rate at which the soup cools is linear, write a rule that would describe the rate of the cooling of the soup. So we could let y equal the number of degrees of cooling. Degrees of cooling in X minutes, we'll say. Degrees of cooling in X minutes. So if y is the number of degrees of cooling in X minutes, then can we write a function rule for this? So we're assuming a constant rate. We had 7 degrees of a drop, and I got that's 210 degrees. It was 210 and it went down to 203 in just 1 minute. Okay, so it had a 7-degree drop in 1 minute. So that would be its rate, right? 7 degrees per minute. So our function, we could say our function is y, the degrees of cooling. So the drop is 7 times the number of minutes. So 7x, y equals 7x. In x minutes, if I multiply that by 7, that's going to be the amount that the soup has cooled off. Okay, so we've written a rule that would describe the rate of cooling of the soup. And so is this a continuous function or a discrete function? Okay, so hopefully you recognize this as a continuous function because our inputs for x could be any amount of time. Any fraction of a minute would make sense in this situation. Okay, so now I'm going to give you a little bit more information. We want our soup to be 147 degrees. We want it to cool to 147 degrees before we eat it. So that would be, if it started at 210, that difference would be 63 degrees. So we want 63 degrees of cooling before we eat our soup. So we could say, well, what number would give us 63 degrees of cooling? What number of minutes? And so we could come over here and solve our, equation for it, or you could just work it out directly too. But 63 is equal to 7 times the number of minutes that we need. So 63 divided by 7 is 9, so x is equal to 9 minutes. 9 minutes of cooling should get us down to 63 degrees. So keeping that in mind, here's some even more information. Here's a cooling table for our function. And So you can see that after 1 minute, it went down to 203. After 2 minutes, it's down to 196. So what was that drop? That drop would be another 7 degrees. Okay, so that's looking good. But then after 3 minutes, it goes down to 190. So that's a drop of 6. After 4 minutes, 184, so another 6. And after 5, another 6. Well, anyway, after 9 minutes, our linear model predicted that it would be at 147. But the actual data shows that after 9 minutes, the soup's at 158. So we could conclude that this data is not linear. So there's not a constant drop in temperature. So it looks like it maybe cooled off faster at first with a couple 7 degrees per minute. But then when you come down here, notice there's just 5. A drop 178 to 173 is 5 degrees. Looks like another 5, 5, and 5. So it's dropping 5 degrees instead of 7 degrees after about 5 minutes. And so we don't have a linear function here. Okay, so even though this this isn't a linear model of cooling, it is still a function, and there still are mathematical rules that can be written for situations like this. And these are the type of functions that you'll be working with more in high school. And I think it's interesting. I'm going to write this on here. The function for this is actually something more like this. For this situation, y, and in this case, y is going to be the temperature of the soup after X minutes. So y is equal to 70 plus 140 times 133 over 140. And you might be saying, where's the X? And it's to the X power. So here X is being used as an exponent, the time, and this would not graph as a linear function. But that's what our data is showing us, is that it's not linear. So anyway, this is an example of a more complicated type of function that you'll be studying in not too many years. Okay, but as I said, this is a continuous function because any fraction of time, any fraction of a minute is going to be an acceptable input for this function. So it's continuous. Okay, here's another type of function. There is a function g, so that the function assigns to each input the number of a particular player, an output that is the player's height. For example, the function g assigns the input 1 to an output of 5'11". Okay, so in the first column, we have the players' numbers. Maybe they're basketball players. Okay, so here's player number 1, number 2, number 3. And then in column number 2, the output is the height of the player. Okay, so this fits the definition of a function because there is a unique output for each input. And, so I could ask you questions like, what number is assigned to, what number does the function assign to player 2? Well, the function assigns 5'4" to player 2. So since each player only has one height, the height they are is the height they are, there's not going to be another number that could be assigned to 2. in this case, or to 3 or 4, whatever the input is. So would there be a formula for this this function rule, this input-output table? Well, there's no mathematical formula, obviously, because it's just heights of different people. So there's no way to really predict, but it still fits the definition of a function. So let's think about whether this would be a discrete or a continuous function. And hopefully you would notice that it's obviously discrete because each of the inputs is separate. There are gaps between the inputs because it's just particular players. And so this is an example of a discrete function, and it's an example of a function that can't be described by an equation or a mathematical rule. Okay, so let's look at your exercises now. So let's look at exercise 1, and you can work on these as you feel comfortable, and then pause and work on them and then come back and check your answers, or we can work on them together here. Okay, so in exercise 1, we have a table that represents a function. So it's a linear function, and it shows how the number of buses is related to the number of students, and what they need for a field trip. So the number of students is our input, and then the function is going to tell us how many buses we need. So for 35 students, we need 1 bus. And then if we have 70 students, we need 2 buses, and so on. So can we write a linear function that represents the number of buses needed, y, for x number of students? Okay, so this is kind of interesting because you notice that definitely it's discrete data, right? Because 1 bus, 2 bus, 3, 4. We can't take half a bus on a trip. If half the bus comes, the whole bus comes, right? So let's write a linear function. So if y, let's see, write a linear function that represents the number of buses needed, y. So y is the number of buses and x is the number of students. So to calculate the number of buses that I need, y, what am I going to do? Well, I'm going to take and multiply. It looks like I need 1 bus for every 35 students, right? So 1 over 35, 1 bus per 35 students times the number of students is going to tell me the number of buses. Okay, so I did that by doing a rate. You could go back if you were not sure what to do there. I could say, since it's constant, right? Every bus holds the same number of students. Y over x, the number of buses to the number of students, is equal to these ratios, 1 bus for 35 students. And then by multiplying both sides by x, we get our function, because the x over x cancels to 1, and we get that y is equal to 1 over 35 times x. Okay, so if you needed a few extra steps to get to that equation, that could be a way you could do it. And I like to just put in some numbers here. If the number of students is 70, and I put in number of students is 70, and I put that in my function here, I get 70 times 1/35, which would be 70 over 35, would be 2. So that would predict the correct number of buses here, and I could check out another one if I wanted to. So are there limitations on x and y? That's question B. What limitations would there be on x and y? Well, X, pen, X would have to be a positive integer. We can't have negative numbers of students, and we don't take half students on trips, right? And Y is also a positive integer. Or I should say non-negative. I guess we could have 0. Positive integer. So no fractions for either these inputs or outputs. All right, so let's look at the next question, which we've already addressed. This function is discrete because if we have integer inputs and outputs, that means there's gaps in between, and so the data is separate. The entire 8th grade student body of 321 students is going on a field trip. What number of buses does our function assign to 321 students? Okay, so our function is y equals 1 over 35 times x, and in this case that's 321. And so y is approximately, it would be 321 divided by 35, and so I get 9.17 and some other digits there. So approximately 9.2 would be a good rounding of that. So 9.2 buses. But we already said we can't have, we need a whole number of buses. And so if we took 9 buses, we'd be leaving someone behind. So our output for 321 is going to equal 10 buses. So we need 10 buses to take 321 students. They're not all going to be full, but that's the minimum we would need to take everybody. Okay, so with discrete functions, you're going to need to interpret your results of your output sometimes. Okay, let's look at the next one. The 7th grade students are going on their own field trip to a different destination, but just 180 are attending. So what number does the function assign to 180? So you go through the same steps. Y is 1 over 35 times 180. Put in 180 for x. And so y is equal to 180 over 35. And that simplifies to, doesn't come out even again. It's approximately 5.1. And since this is a discrete function here, we're going to need to interpret that 5.1. So we're going to use 6 for our output. We need 6 buses to take the 7th graders on their field trip. Okay, so what number does the function assign to 50? Explain what this means and what your answer means. Okay, so when it says, what number does the function assign to 50? That means 50 is our input. And so we have this situation, which is the same as what we've been doing. 1/35 times 50. And so y is approximately 1.4. You probably guess you would need more than 1 bus, but 2 would be more than enough. So the function assigns 1.4 to 50, but since we know the context of this function, we know that we need to round up to 2 buses. So the function, what number does the function assign to 50? The function assigns 2 to 50. well, we could say it either way. The function assigns 1.4 to the input of 50, but we will need 2 buses, something to that effect. Okay, so again, here's an example of a function that we need to interpret. Okay, so let's look at example 2. Okay, so here's another table. This linear function has the table of values below related to the cost of movie tickets. So we're going to have to assume that the cost is constant for any number of tickets. We're shown what the cost is for 3, 6, 9, and 12 tickets. So if we assume it's constant, we can use any of those to find the ratio. So I'm going to choose the first one because it's simplest. So I want to find the unit rate. If it's $27.75 for 3 tickets, then it's $9.25 per ticket. $9.25 per ticket. So our function is going to be the total cost y is equal to the rate per ticket, the unit rate, $9.25 times the number of tickets. So there's our function rule for that. Is this function discrete or continuous? And then you're asked to explain. So the function is discrete, right? Hopefully you saw that. You can't buy half a movie ticket. You can't buy a fraction of it. Therefore, the data are separate. They're integers. So the function is discrete. Okay, function is discrete. You can't have half a ticket. All right, and the last question here. And again, we're just learning all of this function vocabulary and getting used to talking about functions. For that matter, the description for this one would be the total cost of movie tickets is a function of the number of tickets purchased. Okay, they're not asking us to write that, but that's what it would be. What number does the function assign to 4? And what do the question and your answer mean? Well, the function assigns a number to 4. So since total cost is a function of number of tickets bought, 4 is our input. So y is equal to 9.25 times 4. And y is equal to $36. Okay, or not 36, that's actually 36 plus 1, that's 37. 37. 4 times 9 is 36 plus the extra dollar. So $37 for 4 tickets. So what do the question and your answer mean? And you have room to write this. I don't, so you can write something on that. But something to the effect of, the question is saying, what is going to be the total cost for 4 tickets? What is the output if the input is 4? And the answer is going to be my total cost. The function assignment of $37 is my total cost for 4 tickets. Okay, let's look at another one here. Okay, this one is really different. So we have function 3, we have some inputs and outputs. The inputs look like they're all types of fruit. The outputs are colors, right? So can this function be described by a rule using numbers? No, there's no numbers in the table, so I would guess not. So this is kind of like the players and their heights. There isn't really a rule that would define this function. So the question is, no, there's not a number that can There's not a rule that could tell us what color a fruit is going to be. Okay? Describe the assignment of the function. What does the function do? Well, the function assigns a color and we could say it this way, assigns to each fruit its color, right? To each fruit its color. Or, well, I guess we should say the color of its skin, right? The color of its skin. Now, we can't even really say that. We'll go with skin. I don't think strawberries have skin, but that's okay. I think everything else does. So basically, the function assigns to each fruit its own color. And it can't be described with numbers, but it's clearly a function because for each input, there's, exactly one output. Bananas are yellow. Cherries are red. Well, except when they're not. In this world, cherries are always red. Oranges are orange. Tangerines are also orange. And strawberries are red. So even though we had two red fruits here, that doesn't disqualify it from being a function. But each input has its own predictable output. Okay, so state an input and the assignment the function would give to its output. So I could input a lime. If lime is the input, then green is the output. Okay, so there could be a lot of different responses there. Okay, so we're going to do one other example here before we close. And this example is the second problem on your exit ticket. So you can find it on your exit ticket, but I want to talk about it together. So a function produces the following table of values. And each of these, so these are the inputs here. Serious, if serious is the input, adjective is the output. If student is the input, noun is the output. Work, verb, they, pronoun, and so on. Describe the function. So if we were going to describe this function, we can kind of see what the function's doing, right? It's assigning, the function is assigning, here we go. The function assigns a part of speech to a word. Part of speech to each inputted word. To each input word. Okay. So we input a word, the output is the part of speech. And then it says, what part of speech would the function assign to the word continuous? So you got to put on your grammar brain here and think about what the function would assign to the word continuous. But I'm wondering if anybody is having trouble with this, the same trouble I'm having with it. I don't think this is actually a function. And pause the video and see if you can see if you agree with me that this is not a function. This table of values does not represent a function. Would you agree with me that I could put, if I input work, I could get an output of noun? Okay? The work I did this afternoon was difficult. In that sense, the word work is a noun, but it's also a verb. I work on the dishes every night. So words can be two things. A word isn't really a part of speech until you see it in a sentence. And so if somebody agreed with me that these were all valid inputs, this would not be a function, because a given word could have two different outputs. So this would not be a function. Okay, so I've done half your exit ticket for you. So you should say thank you. All right, let's sum up this lesson. Not all functions are linear. We saw a nonlinear function here. It was the cooling of the soup. And not only that, not all functions can be described using numbers or formulas. And we saw that linear functions can have discrete rates and continuous rates. A function that can have only integer inputs is called a discrete function. There's gaps in it. Okay, you can't have those fractions in between. And continuous functions are those whose inputs are any numbers over an interval, including fractional values. So there's no gaps between the inputs in a continuous function. And those are often time. Time is continuous. So, okay. So that's lesson 4. Have fun with the problem set. I've already done half the exit ticket for you, so you are well on your way. Okay, see you back here for lesson 5.